Thank you very much. So welcome everybody. Thank you for joining the third session on LISA instrumentation. This is a parallel session on day 4 to the symposium. Today we will hear from Leah Bischoff from Hanover on the much awaited first performance measurement of the 3 backlink experiment. Then Mattia Vigliani from University of Urbino in Italy will tell us about the relation between simulation of the test mass charging and the measurement on LISA Pathfinder. Then we will hear from Stephen Apple from the University of Florida about the stray electric field measurement, and we'll have a short break. And then we will we'll hear about simulating the micrometeoroid impact on the LISA telescope, my God, and on dimensional stability verification for the LISA telescope, a very important subject. And then from Ada Umiska, the first talk was from Corey Austen, and then Lorenzo Sala will tell us about the last paper from the LISA Pathfinder collaboration about everything we want to know on glitches. The question, as you may know by now, may be filed on the chat. You can even raise hand. However, it is appreciated if you anticipate your question on the chat anyway. And I think that we will see the question can be also asked on YouTube. And all that said, if I didn't forget anything, did I forget anything? No, then we can start with the first talk, which is by Leah Bischoff. Leah, can you try and share your view graph, and I'll give you a warning after 12 minutes, okay?
All right, thank you very much. And I hope you can all hear me and see my slides. Yeah, I'm Leah, and thanks for everyone for listening. I will talk about first measurements and the 3 backlink experiment. And the work I'm presenting is the teamwork from the PRDS team at the AI in Hanover. So let's quickly start with what the backlink in LISA is. So in each spacecraft, we have our 2 optical benches, each in one of the movical optical subassemblies, the MOSAs. And these optical benches need to have an optical connection between them. And this is what we call the backlink, or the phase reference distribution system, in short, PRDS. Since this backlink is part of the critical measurement parse for LISA, it cannot spoil the test mass or reference interferometer in any sense. So any noise that is added from this backlink has to be below the picometer per square root of Hertz requirement. And typically we're talking about the non-reciprocal effects. So since we send light through this backlink in both directions, the non-reciprocal phase, the difference between both directions, is what we call the non-reciprocity, and these effects have to be below the picometer per square root of Hertz requirement. Before I start with the 3 backlink experiment, I would like to give you a short overview about the whole backlink understanding that we have to the present date. So the first investigations for a really LISA-like backlink experiment were done by Roland Flederman quite some years ago, and he used 1 fiber as a backlink and sent light through it in both directions. And he found that this setup is then limited by backscatter, because when you send light in the backlink through both directions, then any light that scatters at the fiber or at the TX fiber will just travel together with the nominal beam in the interferometer. And this backscatter is actually limiting the measurements. So in this experiment by Roland Flederman, this very first implementation with different kind of post-processings, this very high initial noise was reduced to the picometer level. There were further investigations on fiber parameters that are important for the backlink as a fiber by my colleague Max, and there's a very nice pre-recorded talk by him, which I can highly recommend to have a look at. So he investigated fibers, for example, for backscatter, and also for the coupling from temperature to the phase in these fibers. And his results, together with the results by Roland Flederman, were used in simulations, and to understand further what happened in this experiment by Roland Flederman. And they found that the phase noise due to the backscatter is driven by the temperature coupling. In this experiment, it was especially bad because the TX fibers were going through the laboratory where there's a very high thermal environment. So this backscatter problematic in a fiber backlink depends on thermal stability. This is something that we know. And accordingly, the baseline for LISA was chosen based on this knowledge. The design is actually similar to the experiment by Roland Flederman, but with additional improvements like attenuators in front of the TX and the backlink fiber. And the thermal requirement that was derived is a very important part of this baseline. All right, so this was just a rough overview about this understanding that we have. And in parallel, there were also investigations on finding a backlink that has by design less backscatter. And this led to the design of the 3-backlink experiment. And this is an experiment consisting of 2 optical benches, so they can actually be rotated so that we get a LISA-like setup. And they are connected with the 3 different backlink implementation. And the whole design is optimized in backscatter and stray light because we already know from the previous experiment that this is a problem. So one backlink that's implemented here is a direct fiber backlink, and this is the one that is really similar to the one from Roland Flederman and thus also similar to the LISA baseline. Although we have here additional Faraday isolators, and they reduce the backscatter from the TX fiber so that we can actually investigate the backscatter coming from the backlink fiber. A second implementation of a backlink that we have is a free-beam backlink, where we removed the fiber and replaced it with 2 steerable mirrors with a DWS-based control loop. And here, because we have no fiber, we remove the fiber backscatter in this backlink option. And this was implemented in the 3-backlink experiment together with Daniel, and he has a very nice poster presentation on how we did this and all the details about that. The second implementation is the frequency-separated fiber backlink, where we use an additional local oscillator to send through the backlink so that we have the backscatter light or the backscatter interference at a different frequency. The optical bench construction for the backlink was done in Hanover, and this is was a very challenging construction because we have a lot of interferometers and a lot of requirements for each component that we had to place. And my colleague Zhang Ji has a very nice poster presentation on that, which summarizes how we did that. So as I said, we want to measure the non-reciprocity in this experiment, and therefore we overlap the local beam with the backlink beam on both sides and combine the measurements on both sides. And what we get then is a noise term from the fibers and from the lasers in the TX and the TX dot beam. And then we have any kind of physical non-reciprocal effect that happens inside the fiber. We have the phase noise that comes from backscatter, which also has acts as a non-reciprocal effect. And then, of course, we have all kind of readout noise in an experiment. And all of this together is what we measure in our non-reciprocity. So this is all in one term. So this measurement is actually limited by this noise term. And normally in an experiment, you wouldn't use just a reference interferometer to subtract this noise term, but we don't have this here, but we have three backlinks, and they can act as a reference for each other. And therefore, we always combine them pairwise so that we can really measure what we want, so this non-reciprocal term. All right, so this very excitingly is our very first measurement with the 3-backlink experiment with all the 3 backlinks. So you see 3 lines, one for each backlink combination. And you can already see we are way above the 1 picometer requirement, and we are limited here by all kind of readout noise. We have a white noise level at 10 to the minus 4 radian per square root of hertz, and then this increase in the lower frequencies. And in the high frequencies, we were actually limited by a problem inside our phase meter. So we found that the performance was depending on which beat note frequency we are using. So just a phase meter internal problem. And by just choosing a different beat note frequency, we were able to reduce the noise for the direct fiber backlink and the free-beam backlink below the picometer requirement. The third backlink needs 4 different beat note frequency, therefore this is a bit more complicated, but this is not a problem from the backlink, but just from our readouts, so this is something we are working on. Then in the center frequencies, we have this high noise floor due to air fluctuations. So when we evacuate our vacuum chamber, this goes down and we see quite a different kind of noise shape here. And very prominent is the shoulder at 0.14 hertz. And we are very certain that this is laser frequency noise coupling in our measurements. So we can measure the laser frequency noise coupling in each backlink combination. And these are the graphs shown here. And we see the same prominent noise shoulder that we see below here in the non-reciprocities. Very interestingly, we only see it really in the combination that use the direct fiber backlink. So we think that because this is a backlink implementation with a lot of backscatter, that here the coupling works via backscatter. So laser frequency noise couples into a phase measurement with a path length difference here between the backscattered beam and the nominal beam it's interfering with. And this phase of the spurious signal then couples into a phase error on the left and on the right bench. And their difference is what's coupling into the non-reciprocity. And this is what we think we are seeing here. So this looks now like a problem. However, our laser frequency noise at the moment is much higher than we wanted to have in our experiment. So we use 4 lasers. They are stabilized on a reference laser, and they are this is stabilized on an iodine cell. And this stabilization has a problem at the moment, and therefore our laser frequency noise coupling is currently high as this, but with a running stabilization, it should be at least as low as this. And therefore, this is again just a problem in the laboratory that we are working on, because if we can have the stabilization running properly, well, this goes down much. And then also this coupling in the non-reciprocity will be below the picometer requirement. Another reason why we think this is actually due to backscatter is because we can add balance detection to our measurement. And then we see that this noise here is removed or reduced. However, it's just a very little reduction with balance detection. Normally, you would expect that it goes much lower, and therefore we are sure that there's a different noise source underneath that is currently limiting. And there's the cross-coupling issues that we also have in our phase meter, which have a similar shape. And also we see that the noise level here in the center frequencies really depend on our quality of the laser frequency logs. So again, this is some kind of readout problem that we are working on to reduce this noise floor. In the lower frequencies, we think that we are limited by temperature, which, well, as so often in low frequencies, and we can really see that our laboratory temperature couples in our phase measurements. And this is especially bad as soon as we activate our vacuum pumps, because somehow this additional heat load in the laboratory starts oscillations in our air conditioning, which is very unfortunate. So you see that here, a normal lab condition, and then with vacuum pumps running, you see this strong oscillation, which also couple into the sensors inside the vacuum chamber. And when we look at the non-reciprocity, we see here this bump at 2 × 10⁻⁴ Hertz, and here a plot of the temperature sensor measurements. They are basically at the same frequency, so we're very sure that there is some coupling happening. Again, it's mainly happening in the direct fiber backlinks. So we believe it's somehow caused or coupling via backscatter, but we need some further modeling to really make sure that we understand the process. We also see here a temperature measurement for a sensor without the pumps running, so at a much lower level. And therefore, we are convinced that as soon as we, for example, use a house vacuum instead of the turbo pumps, we can also reduce the noise in the non-reciprocity. However, this measurement, I mean, you see we are really way above the requirement here, but it's very interesting because this high noise level allows us to probe on our understanding of the temperature to phase coupling in a backlink. And when we change the laboratory environment by using the pumps differently, changing the heat load, we will be able to have these measurements at different kind of temperature environments, and then we can really study our model on how this temperature to phase coupling in a backlink works. So, I mean, this is kind of a problem, but it's also kind of a nice opportunity. All right, so I showed you how we started with a measurement with a lot of noise, and showed you a little bit on what we did.
3 minutes to go.
All right, thank you very much. Yes. We reduced the noise in the high and in the center frequencies. And what you see here is our measurements, like our best measurements without any post-processing compared to the measurement by Roland Flederman. And you see that the goal of this debacking experiment to reduce the backscatter by design was already successful in these frequency ranges. We are quite sure that what we are seeing is some kind of readout and laboratory problem noise, and that's things that we are working on. For now, we can already say that the lines that I'm showing here are the upper limit for a backlink performance for a backlink that is operated under a temperature stability of 10⁻⁵ Kelvin per square root of Hertz. So the backlink experiment, the goal is to bring the noise floor to the 1 picometer per square root of hertz requirement. And then we can really investigate the backlinks for their performances. We have a lot of details like the rotation. We have 2 benches. We have 3 different backlinks, which allow us to disentangle the noise sources. And we have many possibilities for future measurements in order to study the backlinks and all kinds of parameters. One thing that we can do is to enhance the temperature environment to study our model from temperature to phase coupling. Except for this very high temperature stability of our backlink fiber, which is inside the vacuum chamber, the rest of the design and the components of the 3 backlink experiment are a worst case study for LISA. So therefore, this is very helpful. Currently, we have an understanding of our laboratory noise, and we are working on improving that. So to summarize, I gave you first an overview about our understanding and the investigations that have been done and are still ongoing on really understanding how a backlink in LISA works. And this gives us confidence in the LISA baseline that was derived from these investigations. I also introduced to you the 3 backlink experiment and showed you our first measurements and gave you the first understanding of our noise floor and how we plan to improve this noise floor. And as I just also introduced, as soon as the noise floor is low enough, we will be really able to probe all 3 backlink implementations for their non-reciprocal behavior. And yeah, thank you very much.
Thank you, Leah. Very interesting and very sharp on time. So, question. I have a question from Dave Robertson. I missed why having the pump on increases the temperature noise.
It's a problem in our air conditioning. So somehow the heat load in the lab is higher, and it's not supposed to do that. It's yeah, it's a problem in the air conditioning.
Then I have
it's going to be fixed.
I have a question from Harry. Harry, why don't you ask the question directly?
Sure. Hang on.
It's a long one to read.
It was a question, if you can hear me, about how you are certain that the coupling of the low frequency room temperature fluctuations is directly acting or directly coupled via its action on the fiber rather than on some other aspect of the overall rather complicated setup.
So I mean, this is why I also said we need some more modeling to really be sure on how the coupling works. So I mean, there are even different points in the fibers where it can couple. So it can couple in the feed-through fibers. We definitely see that. And then it's a question of how good the common mode subtraction is, if that really is removed in the combination, because it should cancel in the non-reciprocity. And then there is the effect that it couples in the backlink fiber itself. And then, yeah, as you said, there are also other points where it can couple, but we think that the current model that we have is, it explains this, but it's not finalized. So this is why I didn't show this in more detail here, because I didn't want to show such a preliminary modeling. Hope that
thank you. It'll be good once you are able to not have the vacuum pump on, so that we see that there isn't any other layer of noise below what you see. That would be very comforting.
Absolutely. That's
thank you.
One of the next steps.
Thank you. Any other question? I have one question. Maybe I'm confused. I didn't get something. But by comparing the 3 link, aren't you always limited by the worst one?
Yes, that's absolutely true.
So if the LISA link is the best one, we could never know. We could, from your experiment, we wouldn't know.
Yeah, I mean, if the other ones perform bad, of course, but I mean, all of them were chosen in a way that they are expected to perform well enough. And so far, we didn't found any reason why one of the others would be worse than the LISA-like one. So, but it's true. Yeah, we can always only say it's a limit.
Then I have a question from Antoine Petitot. Antoine, please ask your question.
Yes, maybe I misunderstood something. A very nice talk. Thank you very much. But maybe I misunderstood something. Did you say that there is a link or a link between the noise and the bit note frequency, or it was something that you mentioned in one of your first slides? And you know that in LISA, the bit note frequency will evolve with time. So are we expecting that the backlink noise will vary with time because of this variation of the bit note frequency, or it's something that we can remove and it was just in your experiment?
No, we are very sure that this is just a problem inside our phase meter actually, so it's not connected to the backlink.
Okay. So
but
we are not
just,
expecting this for Lisa.
no.
Good.
But I mean, good point. I can understand where
Cross
this was.
finger.
I mean, yeah, from my view, of course.
Okay, thank you.
Thank you. Other questions for Leah in this nice work? No. If not, well, thank you again, Leah. Thank you very much
Yeah,
for this
thank you
nice
for listening.
talk. And now we move to Mattia Villani, which is going to talk us about the bridging the gap between the pre-launch simulation and the measurement on board LISA Pathfinder, right?
Yes,
Thank you,
exactly.
Mattia. I'll give you a warning at 3 minutes before the end of your talk.
Okay. Good morning, everybody. I'm talking about the new simulation we carried out in Urbino University with our new Monte Carlo toolkit in order to simulate the test mass charging for LISA Pathfinder and compare these results with the measurements carried out on board LISA. LISA Pathfinder was an ESA mission, a demonstrator satellite for the technology that we place on board LISA. It was launched on December 2015. It reached the L1 at the end of January 2016 and it operated until July 2017. The main aim of this mission was to study the noise budget of the instrument that will be placed on board LISA. And among these noises, there is the test mass charging due to the galactic cosmic rays and solar energetic particles. When talking about charging, there are two notions that are important. One is that of net charge, which is the algebraic sum of the charge deposited on the test masses. Here is the formula where J is the charge deposited and lambda J is the rate of the deposition. Then there is the effective charge, which is the sum of the square of the deposited charge. So there is a J square in the formula. LISA Pathfinder flew on the declining phase of the solar cycle 24. Here is the beginning of the mission, here is the end. The modulation of the galactic cosmic rays are reported here in this plot. At the beginning, it was this continuous curve for proton and helium. At the end of the mission, it was the dashed curve. And when the measurements were carried out, or test mass charging were carried out, it was this dotted curve. LISA will fly in the ascending phase of the solar cycle 26 with a similar solar modulation of LISA Pathfinder. In our simulation, we did not consider particles with energy below 100 MeV because they give no charging to the test masses. For more information on the SEP and the galactic cosmic rays, see the recorded talk by Category Mani. The pre-launch simulations carried out in 2015 gave this result. So the net charge was constrained between 14 and 32 charges per second, where the effective charging was confined between 170 and 300 charges per second. On April 2016, when the measures were carried out, they found that the test mass net charging was 23 charges per second. So it was well constrained by the simulations. While the effective charging was wrong, resulted underestimated by a factor 3-4, even including a contribution from other particles, which is about 15%. This is due to the fact that simulations were carried out with Fluka and GM4. This toolkit have a low energy cutoff for secondary particle propagation, and this is done to reduce the computation time. Fluka has a cutoff at 1 keV for all secondaries, and GM4 in 2015 it had a cutoff at 250 electron volt. Now with the new option 4, the limit is set to 100 electron volts. Among these low energy particles, there are low energy electrons, which were neglected in these early day simulations. But the point is that LISA Pathfinder and LISA will be very sensitive experiments. So low energy electrons cannot be neglected. In this context, the European Space Agency found it necessary to call an ITT with the aim to build a toolkit for the simulations, which for the simulation of test mass charging, which included low energy electrons. We as Urbino University are participating to this ITT with the Trento University and OHB Italy. So in order to include all the low energy electrons, we had to carried out a survey on low energy electromagnetic physics. And we found that the most important processes are low energy ionization and kinetic emission, which is the production of electrons by a surface bombarded by charged particles. We also considered transition radiation and Bremsstrahlung, but we found that their contribution is negligible. Moreover, one has to consider the fact that at low energy, electrons behave like waves. So quantum processes must also be considered, and these processes are electron diffraction and quantum backscattering. All these previous processes were included in the new Monte Carlo program LEI, which was developed at the Urbino University. LEI is thought to work alongside with LUCA. LUCA propagates all primaries and secondary particles in the LISA Pathfinder satellite geometry up to the last 150 nanometer layer of coating of the electrons and test masses. All these charged particles are propagated by LEI in this 150 nanometer layer, producing and propagating low energy secondary electrons in the range from 10 electron volts to 1 keV. Why 150 nanometer? This was chosen as a compromise because in our simulation we need to include all the low energy electrons, but these low energy electrons are millions, so we need to keep the CPU time under control, and this means that we had to reduce the thickness of the layer, and we found that 150 nanometer was a good compromise. The full geometry of LISA Pathfinder was implemented in FLUCA with the program FLARE. Here is the CAD of the geometry. On the right, there is a zoom on the central region, which is the LISA technology package. Each of the two columns are the vacuum enclosure. The pink cube are the electrode housing. The blue part are the electrodes. The yellow is the test mass, and this is the optical bench. During the LISA Pathfinder mission, no SEP event with a flux above the background of galactic cosmic rays was detected. So in order to test the effect of SEP on LISA, we had to consider 3 historical SEPs. We chose one from the 1956, which is a very strong event measured on the ground with a neutron monitor, and 2 from 2006 measured in space by Pamela, which are weaker. Here on the left, we see the flux of these sets compared with that of protons and helium from galactic cosmic rays. This is the flux at the onset of the SEP for 1956, and we see that it is already 3-4 orders of magnitude larger than those of galactic cosmic rays. But the peak reached a peak of about 7 orders of magnitude larger of the galactic cosmic rays. This is the weaker event from 13 December of 2006, which reached a flux of about 4 orders of magnitude larger than those of galactic cosmic rays. This is the weaker event we considered, which is about 2 orders of magnitude larger than the galactic cosmic rays. Here on the right, we see our result for the simulations. We see that apart from the very weak event, which gives a charging comparable to that of galactic cosmic rays, the other 2 SEP events give a charging of the order of thousands, or 1,000 charges per second, and the peak of the large event gives a charging of 130 million charges per second. Then we simulated the solar maximum and solar minimum, considering protons, helium-3, helium-4, nitrogen, carbon, oxygen, iron, and electrons. We see that the largest, in the net charge, we see that the largest contribute is from protons, then follows those from helium, and a large negative contribution from electron, which essentially erases that of helium. So in the end, the charging was about that of protons. Similarly, for the effective charging, we see that the protons give again the largest contribution, and that in this case, nuclei give a contribution non-negligible, of the order of 20% of the total. And in the end, we found that at solar minimum, the effective charging was 1530. Similar things can be said about the solar maximum, where the total net charge was 4.6 charges per second, and the effective charging 620 charges per second. Then we carried out a simulation for April 2016, when the measurements were carried out on board LISA. We considered protons, helium, and electrons. We see that the net charge resulted 22 charges per second, very close to the 23-24 charges per second measured on board LISA Pathfinder. And the effective charge resulted in 933.34, which is very close to the 1,1300 measured on board LISA Pathfinder. Based on solar max and solar minimum simulation I showed in the slide before, one should add to the effective charging a contribution of about 15-20%, bringing our result even closer to the actual measurement. So for my conclusion, that Monte Carlo toolkit GN4 and Fluka have a low energy cutoff to reduce the computation time, and therefore, as a result, neglect low energy electrons. This resulted in an underestimation of the effective charging in the early day simulations. With our new Monte Carlo toolkit lay, which allows for the production and propagation of low energy electrons down to 10 electron volts, we have filled the gap between the measurements and the effective charging, the estimated effective charging. So that was it. Thank you for your attention.
Thank you very much, Mattia. This was shorter than the time allowed, but very, very interesting. So, question for Mattia. While we wait the people to come up, I have a question, but now I'm confused, because I thought that the mismatch between the old simulation and what we saw in LISA Pathfinder was almost a factor 2, but we are saying that the electrons is something like, what is this, roughly 20% is, the electrons are completely neglecting the electrons made us make a mistake of 20. And the rest is coming from helium. Wasn't helium included in the old simulation?
This is the old simulation. You see that the old simulation gave effective charging for 170 for the solar minimum, and 256 for, no, the end, contrary. 170 for the solar maximum and 300 for the solar minimum.
And Pathfinder was somewhere in between?
LISA Pathfinder was...
No, that's what we found, but the original prediction for April 2016 would have been a number in between P min and P max, right?
Should have been, yes. Should have been a number here in between, yes. But it was 1,000.
So this is a pretty significant underestimate. This is not completely explained by electrons, right?
No, why? With our simulation, you see that this is 933, and the simulation is
you're now fitting the observation, but the protons are more than we were expecting. I see Tim Sumner is making a comment. Tim, do you want to comment?
Yes, you might as well finish the point you're already discussing first, though.
Yeah, no. It looks to me that the simulation now increase also the number of protons, right? They give a larger number of protons, a larger number of helium, or maybe I'm mistaken.
Well, if I can add something, because at that time Matteo was not here, so he was not here, so he didn't follow the details of these early days simulations. Of course, when we have carried out these first simulations, we didn't know which kind of galactic cosmic rays we were going to face in the spring 2016. So we made some predictions for the first part of the mission, the very first part of the mission, like the end of 2015, minimum, maximum predictions for that period. And of course, we now know that exactly what the flux was, because we have the data from AMS-DIV2.
Okay. Tim, do you want to complete your comment?
Yes, okay. I'd first like to correct something that was said earlier on, that the low energy electrons were neglected in the original study. In fact, they weren't. There was an extensive discussion of them in the Araujo paper of 2005. And because of that, there were experiments done on LISA Pathfinder that explicitly looked for these low energy electrons by altering the bias on the test mass, because you would expect to see a dependence of the charging rate on the bias of any bias on the test mass. And one was a dependency was seen, but I believe it not be compatible with such a large noise rate, additional noise rate from the electrons. So I wonder whether you've looked at that additional constraint from the bias versus charging rate data from LISA Pathfinder.
So we did this extensive study on the processes that produce low energy electrons, and we found that these low energy ionization and kinetic emission were the most important.
So the question is, would the bias be relevant here? On any voltage bias on the test mass will be of big relevance?
Well, I come again because, again, this, I'm not sure if Mattia knows this. We have discussed this a lot with Valerio about the possibility to make basically negligible, if not zero, the charging. I'm not sure if this is the question. The charging on board. Is this the question? So with proper, you know,
well,
voltage.
Yes, if I could explain a bit further, the kinetic emission electrons are low energy. They're with a work function of about 4.5 electron volts on the surfaces. All the electrons will be sort of, you know, around that energy, even lower. So so when you start to bias the test mass up to a volt, you will alter you'll alter the transfer of electrons in both directions, either from the housing to the test mass or from the test mass to the housing. And that will give you a measured change in the charging rate as a function of the bias on the test mass. We're just finishing the paper on that for those data to be published. And that dependency on the voltage actually puts a constraint on how many secondary electrons can be present. And I think our conclusion is that you can't get up to the noise level that you need because of that constraint. So that constraint turns out to be critical to the discussion, I think.
Okay, sure.
Thank you, Tim. Thank you, everybody. I think this is becoming very.
This is just a matter of
any other question? Thank you, Katia. Any other question for Mattia? If not, let's thank Mattia again. This was a great talk. Thank you very much. Okay, and now the next one is from Stephen Apple from University of Florida, Gainesville, on the measurement of stray electric field via test mass charge modulation. Let's go. Thank you. And I'll give you a call 3 minutes before the end, okay?
Okay, great, thanks. Yeah, thank you for the introduction there. Can everyone see my screen okay?
Yes, perfect.
Okay, great, yeah. Thanks for coming, everyone. Today I'll just be talking about some of the work we've done at the University of Florida about demonstrating the measurement of stray electric fields via test mass charge modulation. So I think all of us are probably pretty familiar with the GRS at this point, but just as a quick overview, the LISA gravitational reference sensor, or GRS, provides a reference for the local inertial frame. You can see a picture of the Pathfinder GRS on the right here, and it consists of its free-floating test mass, its housing, and its actuation and sensing components, along with its associated electronics. And it also includes UV light injectors for a contact-free method of test mass charge management, which you can see kind of on the corners here, these light injectors. So yeah, overall, the GRS, along with LISA's drag-free control system, will help provide an ultra-quiet environment for the test mass, such that it's following a purely geodesic orbit and free-floating. So today I'll be talking about one source of noise on a LISA GRS, which is stray electric fields in the sensor. And stray electric fields can couple with an electric charge on the test mass and create a force that perturbs the test mass from its purely geodesic orbit. So the test mass and electrode housing surfaces have patch effects, which are caused by spatial variation in the electrostatic potential across the surfaces due to contamination of the gold surfaces. And these patch effects, combined with the voltage offsets in the electronics connected to the sensor's electrodes, can cause these stray electric fields. So very important to have a means of measuring and compensating for these stray electric fields in the sensor. And these stray electric fields are typically modeled as this delta X term here. And this term is basically the equivalent potential that you would have to apply to a single X electrode to produce the same force on the test mass as the stray electric field. So with LISA, the delta X must be measured with a calibration procedure where you essentially measure the force response and the sensitive degree of freedom for a given stimulus in the test mass charge. And once the delta X is measured, DC biases can be applied to electrodes in the sensitive degree of freedom to compensate for that delta X. And one method of measuring delta X that's been demonstrated both on the University of Trento torsion pendulum and on LISA Pathfinder was a DC method in which UV light was shined at the test mass or electrode housing surfaces to produce step changes in the test mass charge and measure the resulting force on the test mass. And with this technique that I'll be describing today, the test mass charge is modulated by shining pulsed UV light that's synchronized with an oscillating potential induced on the test mass with surrounding electrodes. And that's kind of illustrated in this cartoon here on the right, where the black curve is that oscillating potential induced on the test mass, and the purple square wave is the pulsed UV light that's synchronized with that oscillating potential. And some of the advantages of this charge modulation technique are that it's faster, more easily automated. The sensitivity can be optimized by choosing a modulation frequency where the sensor is more sensitive. And it also allows for the possibility of measuring delta X on multiple test masses simultaneously by choosing different modulation frequencies. All right, so we've demonstrated this method of measuring delta X on our torsion pendulum facility at the University of Florida. And you can see a picture of our facility here. The pendulum kind of lives in this thermal enclosure. And if you were to look inside the thermal enclosure, you would see our vacuum chamber. And inside that vacuum chamber, we have our torsion pendulum. So this picture is showing a CAD rendering of the pendulum inside the chamber. The pendulum consists of this crossbar assembly suspended by this 1 meter long, 50 micrometer in diameter tungsten fiber. And in this picture here, you can see our unsuspended crossbar a little bit better. So the crossbar includes 4 hollow LISA test mass mockups. at each of its ends. You can see two of them here, and the other two are inside their electrode housings. And the low thermal noise of the fiber, along with the light-weighted test masses, make it so that the pendulum is extremely sensitive to forces acting on the test masses. And this essentially gives us a near free fall condition in 1 degree of freedom. So the two test masses that are enclosed in these electrode housings are our gravitational reference sensors. We have a simplified sensor, and then we have a LISA-like sensor, which was the design was based off the LISA Pathfinder GRS. So it includes 18 electrodes for 6 degrees of freedom in actuation and sensing. And it includes 3 UV light injectors for UV LED-based charge management. So with the pendulum, we have 2 methods of measuring the position of our test masses. One is a capacitive readout scheme, which is similar to the LISA Pathfinder capacitive readout scheme. So with this method, the GRS measures the position of the test masses by measuring the position-dependent capacitance of a set of electrodes toward the test mass. And this is done by polarizing the test mass with a 100 kilohertz injection signal sent to electrodes in the GRS. And then these electrodes are, and then we read out the voltage from a pair of sensing electrodes connected to our readout electronics. And this voltage that we read out from these sensing electrodes is proportional to the test mass displacement. So in addition to the capacitive readout, we also have laser interferometer readout. Our interferometer is a polarization multiplex Mach-Zehnder interferometer, and this provides differential position readout of our test masses. And for the experiments that I'll be talking about today, we use the laser interferometer data and our LISA-like GRS. Okay, so moving along. So for these experiments, we used a prototype UV light unit provided by the UF Charge Management System Group. And this unit allowed us to generate UV light pulses synchronized with the sensor's 100 kilohertz capacitive sensing bias. And then we were able to linearly vary the phase of the pulsed UV light with respect to that 100 kilohertz signal to modulate the charge of the test mass at 1 millihertz. So this image on the right here is showing kind of the setup for the experiment. So this is our sensor. You can see in this experiment, we have one UV light injector, which this UV light injector 1 here, which is used to modulate the charge of the test mass. Then we have a second UV light injector that is being shined at a constant phase and just being used to compensate for the non-zero equilibrium potential and eliminate forces resulting from the coupling of the average test mass potential with its modulating component. So also shown here, you can see our signal being applied to these X electrodes here, this 12.3 millihertz signal. And this is the signal that we're applying to make our charge measurement. So essentially we have equal and opposite voltages being applied to our X electrodes. So that would be this 1 volt, 12.3 millihertz. So you can see 2 of our X electrodes here. And then on the opposite side, we have our other pair of X electrodes, which are receiving the equal and opposite potential for that charge measurement. And also in this picture, you can see these blue electrodes are our injection electrodes that are receiving that 100 kilohertz signal. So this plot here is showing our data from our experiment. You can see in the blue points here are our measured charge from the sensors. So we have test mass potential on the y-axis versus time. So this is our charge measurement at that 12.3 millihertz. And you can see that we are modulating the test mass potential at the 1 millihertz. And the bottom plot is just showing how we were linearly varying the phase of the UV light to produce this test mass charge modulation. All right, so after we successfully modulated the test mass potential, we were then able to demodulate the pendulum data to obtain the amplitude of the test mass charge, as well as the amplitude of the resulting force at our 1 megahertz modulation frequency. And from this, we were able to calculate our delta X, or the stray electric field in the sensor. So we repeated this modulation experiment for 5 different DC compensation potentials applied to the X electrodes. And each of these measurements was conducted for a duration of 10,000 seconds. So that's what this plot is showing on the right here. This is the measured delta X for each of those compensation potentials. And we also have our linear fit to the data. So we were able to use our zero compensation intercept here, so of our linear fit, to effectively find the delta X in the sensor. And this gave us a delta X of this 328.2 millivolts plus or minus 0.2 millivolts. And we also found that we got a test mass modulation, test mass potential modulation of around 133 to 136 millivolts for the compensation potentials we applied. And we also measured forces in the X direction on the test mass of up to 25 piconewtons with a precision of about 20 femtonewtons. Okay, so yeah, just to wrap up really quickly, this novel charge modulation technique, we've demonstrated that we can, this is an effective technique for measuring the stray electric field in a GRS with sufficient precision to compensate and suppress random test mass charging noise. And again, just some of the advantages of this technique are that the sensitivity of the measurement can be orders of magnitude better than DC methods if you choose your frequency in the sensitive band of the sensor. And in principle, you could measure the delta X on multiple test masses by choosing different modulation frequencies. And it also offers some significant time savings over DC methods. And we actually have a paper that is coming out soon. It's under review at the moment, but that will be in Physical Review D. And that goes into much more detail about these experiments. Yeah, I think that'll wrap it up for me. I'm happy to take any questions.
Thank you very much. Yes, indeed. Very interesting experiment and very nice talk. So, question for Stephen. Either in the chat or through YouTube, while you get rid of your shyness. Let me ask one question. So you found a native delta X on your test mass of 300 millivolt?
Yeah, yes.
Wow, that's big. Is a third of a volt. That's surprising. Do you know why? Is that what was like the treatment of your test mass surface? Or I mean, my experience is that we're talking tens of millivolts, not 100 millivolts. So, but maybe, maybe it's just random. But you have an idea why the number is so big?
I'm not quite sure. So the treatment of the test masses, I guess, would be similar to, I guess, what would be expected with Pathfinder. So we just have the surfaces of the sensor and the test masses are polished to a mirror-like finish and then gold coated. And yeah, so similar treatment, I guess, to what would be expected with the sensor. So I'm not quite sure why, why that would be, I guess, larger than expected.
Never mind, it was just a curiosity. It may depend on so many things. So.
Right.
So other questions? People are shy today. Or maybe you are too clear. Well, I don't see any other. Well, then thank you very much. And thank you all the speakers this first half. And now, if I'm not mistaken, we have a break till 4:15. Is that right? Where is my support?
Yeah, that's correct. Yeah.
Okay, so let's reconvene at 4:15, maybe a minute before, and we'll go into the second half of the session. Thank you all. Enjoy your break.